Yes,
Okay.
Bhaiya.
Okay. So, I mean, yes, people complain a lot about, the quality of the education that they're receiving. Like, what if we had better teachers and what if we had better material? So, I'll teach you from material from the IITs and ISC and like top universities in the world. The only challenge is can you keep up with what is being taught? So, I don't know if many of you went over part one of the video. Did anyone see the first video that I linked in the message that day? That was part one of this. It was before some of you joined PB. So some of the people here were there for that session. That was on an intro. So anyway, even if I had to like very quickly skim over that, maybe in like 5 minutes, we can definitely do that so that we can like give a refresher to everyone. So basically, computer architecture and computer organization is the study of how computers actually work, as in how you go from electricity all the way up to your modern day processors, from ones and zeros to full-fledged operating systems and compilers and everything else. So the few things to remember is that systems have gotten a lot faster. Basically, you could think of it as this way: if transportation uh, improved the way that computers have improved over the last few decades, then it would be possible to go from somewhere like New York to Mumbai in a few seconds for a few paise or a few rupees, like 2 or 3 rupees. So that gives you an idea of how much systems have improved. They've improved by a factor of many thousands and many lakhs or millions compared to this thing. And it's all underpinned by a law known as Moore's Law, which says that the amount of transistors are the chips that systems have that have zeros and that are responsible for zeros and ones. They double in size in a given chip area every 18 months. So uh, uh, for a while, all the way up till 2006, computers really did become twice as fast every 1.5 years. Uh, and that was a pretty crazy period of time. Unfortunately, the speed of systems is no longer increasing that fast now. Computers that, I mean, people that have laptops 4 years or 5 years old will find that, most of those laptops are perfectly functional for a large variety of everyday tasks even today. So there is a slowdown, but there's also a speed up in many other ways, and there's more than one way to measure the speed of a system. So let's dive into that. So basically, we started with really big systems and we moved to smaller systems, and now we're in the handheld era where we have handheld systems. So all of this is underpinned by about 8 ideas. One is that design for Moore's law, which is if you're making software today, you have to design it for the hardware of tomorrow. Otherwise, you'll be selling yourself short. The biggest example of this is game developers. When they make a game today, it when something like GTA 6 would have started development like 6 7 years ago, and the systems 6 7 years ago are much less powerful than the systems today. Yet when GTA 6 comes out later this year, even the newest hardware will not be able to run it at full settings because they want to have the maximum visual quality possible. They wanted to take advantage of all of the hardware that's there, and that means designing your systems for tomorrow, which means in practical terms, if you are writing software now, and if your software is heavy especially and it requires a lot of resources, then if you're not able to take advantage of parallelism, if you're not able to take advantage of the fact that all computers today, whether it's a mobile or your laptop or your PC, it has multiple cores, right? It has multiple cores and it has lots of RAM. If you can't use that to give your user a better experience, faster load times, and a better UI or interface, then you are losing out. You have to use abstraction to simplify design, which means that lower parts of your system, the parts that build up, make up your system, have to be abstracted away. As we'll come to see, there's a lot of complications involved in designing a system, and those abstractions they enable you to build more powerful systems by assuming that the underlying units are monolithic blocks, making the common case fast. Performance via parallelism is again via multiple cores, via pipelining is taking advantage of executing instructions of one after the other. Prediction is when your CPU decides to execute certain instructions even when it knows that even when it's not sure whether those instructions will be executed or not. Then there's the hierarchy of memories, and finally dependability via hierarchy of memories is of course your cache, RAM, registers, cache, RAM, primary storage, secondary storage, and then redundancy is multiple units of the same system to make sure that your system is fault proof. So the slides that I'm using are the slides for a book called Hennessy and Patterson. It's the book that I think everybody who's ever studied CS should read at some point. It's a really, really good book, and it teaches you everything about computers. So, uh, one more thing that is closely tied to architecture is, of course, the execution of programs, because ultimately a computer is what is a computer if not a system that can execute arbitrary programs, right? So, we'll go into that as well. We'll learn about all of these abstractions. Like, for example, this is the Apple A5 chip, and as you can see, it's quite complicated. This is a SoC, which is a system on chip, means it's much more than just the CPU. You can see it has I/O blocks for the touchscreen and the digitizer and everything else. It has general purpose input output pins which form the PCI bus and other interfaces. There's USB, there's a slot for the memory. There are multiple data paths and multiple processors. So this is a fairly complicated beast, and modern day processors are again very finicky things that take advantage of everything from quantum mechanics to physical phenomena to do what they do. And so we'll go through that as well. So this is a little bit about the manufacturing performance and how to measure the performance of a system, right? So there are different things like bandwidth and through. There's a different metrics like latency, ping, and throughput. So if you had to tell the difference, like if you're playing a game, how fast you're able to receive a response, or how fast you're able to your data is being transmitted with how much latency, that is your ping or latency. So that's like the round trip. Whereas if you're downloading a movie, how much bulk data can you download in a second or a minute in terms of mbps or capital mbps, which uh, or gbps or whatever is your bandwidth or throughput. So both of them are different numbers. So first thing that we'll look into, continuing from here, is the processor, okay, the CPU. So the performance of a CPU is measured by a bunch of different things. One is something known as the instruction set architecture, and the other is the compiler. So the instruction set architecture broadly is the set of instructions that a CPU produces, and this looks very different based on what you're running. So let's take a look at some instruction set architectures, like how the same program's assembly can look very different for different systems. So let me just load up Godbolt on this side until it loads up. And of course, it's also determined by your compiler. Basically, if you run a better compiler that produces better code on a system that can take more advantage of the features of the system, you can get more performance out of the processor. This is because every year when new processors are launched, they're not like automatically faster, right? You have to build software that takes advantage of that hardware, and that might come in the form of new instructions, like certain kinds of vector instructions or scalar instructions. It might be new additions to the instruction set. So let me see if this is loading up. So see, quite a few more people have joined. That's nice to see. Let- Is my luckily this thing isn't on, so should load up eventually. Okay, good. So this is a tool known as Compiler Explorer. I've given a talk on Compiler Explorer before. You can go check it out if you want. So like basically here we have a program on the left side, and this is the corresponding assembly on the right side. So this program is a matrix multiplication program. Okay, it takes two big matrices and multiplies them. It's a very optimized matrix multiplication program. So it'll look very complicated. Maybe the code will look complicated and the assembly will look complicated. But at the end of the day, you're just multiplying two matrices. It's something that we've all done, right? So here you can see the assembly here that there's these instructions like push, sub, move, uh, load effective address, move ABS. So one good thing in Compiler Explorer is you can just hover over the instruction to see what it means. So for example, this move ABS means copy the second operand with the first or to the first operand. So this is like just an absolute copy instruction. The JL is to check the state of one or more flags. CMP is to compare. So jump and compare together form a loop basically. So you can see that these instructions look like this. So this is because I have x64 Clang. Basically, it's the compiler for what you call like x86 processors, so Intel and AMD processors. So now I might choose to load up some other type of Clang. So let's say ARM based this thing, right? So let me load up ARM v7 Clang. So this is for the ARM compiler, which is what your stuff like your Raspberry Pi and others have. So suddenly you can see that the assembly looks very different. There's much shorter instructions, and all of them have very regular formats. So we push LDR, add LDR, STR, ORR. All of this stuff wasn't there before, right? So basically, we have the same C++ program. We didn't change the program, but the assembly is totally different. Basically, if the assembly represents the way the program runs on the hardware, then basically we have changed the way that basically the instructions that we need to run to make this matrix multiplication program execute on ARM is completely different from the instructions needed to execute it on x86. And this is the reason why you cannot run like software designed for ARM on x86 and vice versa. So basically, like you can have a Raspberry Pi that's running Ubuntu, and you can have a normal laptop, Intel or AMD laptop that's running Ubuntu, but both of them will look like they're running the same Linux operating system. But you cannot copy an executable from one of those systems and run it on the other system just like that. You will have to recompile it for the new target. So instruction set architecture matters. It defines the set of instructions that a system executes, right? So CPI and cycle time. So the CPI is the cycles per instruction, and the cycle time is how long the processor takes to execute one cycle. So obviously this is important. 5 gigahertz processor will run 5 into 10 power 9 operations per second, whereas a 4 gigahertz processor will run 4 into 10 power 9 operations per second. So if all other factors are the same, the 5 gigahertz processor will be faster than the 4 gigahertz one because it will have a shorter cycle time. The cycles per instruction depend heavily on the architecture itself. So x86, for example, it's very famous for having some really complicated instructions that do a lot of things in one cycle, but I mean, they can be hard to complete. So like there are some instructions like which take like the 128-bit words and chop them up into 8 pieces and then add them in parallel. But those kind of instructions take multiple cycles to run, whereas the ARM, which is based on the RISC architecture, like a reduced instruction set architecture, that runs faster because the instructions are simpler. So you might already see this here also that all of the instructions are the same format. Like there is one instruction, there is like some register here, and there is either like a destination or there is an address. So it is basically four fields. Everything is always four fields. So this is one feature about ARM, that it's either four or less than four. Whereas if you look at x86, again, it's a lot more complicated. So if we go to x86 clang, let's take the trunk clang, which is the top, like the latest compiler that's available on x86 side. You can see here that there are some really weird things that are happening, and there are some really long instructions. So there's a function call, and there's one instruction where like five, six different things are happening. So x86 is a more complex instruction set. It's not complex by design, unfortunately, because it was not designed as such. It evolved over a period of time. So there are a lot of compromises and hacked on things that are there. Whereas ARM is just a simpler architecture because when ARM came out, they had the advantage of knowing like which direction CPUs are going in, and the architects were able to figure out that if we go for a simpler design with simpler instructions. So one example I can give is ARM does not have a divide instruction. ARM also does not have a subtract instruction. ARM just uses negative, like reverses the sign of the numbers and add them together. So if you do like 2 minus 9, the ARM compiler on ARM side, you will just do plus 2 plus minus 9. So instead of calling a separate subtract instruction. So it does these kind of shortcuts. There's also fused multiply add, which fuses a multiplication and an addition together. So there are these types of instructions in ARM. So here we'll take a look at something called the MIPS architecture because it's very simple and easy to understand, right? So instruction execution in a processor. If you have a processor, basically how do instructions execute? And by instructions, I mean each of this, what do you call it? Move, push, move, sub, whatever. All of these instructions have to execute one by one by one at the end of the day, right? So how do they execute? You have four parts. You have something known as a program counter. Okay. Then you have something known as instruction memory. Then you have registers. Then you have the ALU, which is the arithmetic and logical unit. And then you have something known as the data memory. So these are the various parts of the CPU. And why they're designed this way is because you have to take certain things in. So let's say that I have four parts. Okay, I will execute this one by one. So first thing is I need to know which instruction to execute. So for this, which instruction to execute, I'm going to use something called the program counter. That program counter's job is to fetch the next instruction from the top of the stack and push it in. right? So it will fetch the instruction. This step is known as instruction fetch. Then your register is what stores the data in the CPU. So each the CPU has something between like 32 to 64 registers, which can all store values. And the ALU is what actually does the math and comparisons. So it's called arithmetic and logical unit because it can do add, subtract, multiply, divide, modulus, and it can also do greater than, lesser than, such that stuff like that. Uh, and then if you have to store some data as a result of that, for example, you did add of two instructions and you want to store the result in some third register, you have to store it in the data memory, otherwise you can skip that. So, and then by the time that the instruction reaches there, your program counter is already pointing towards the next instruction to execute. So, at this point, if you have any questions, you can stop and ask, otherwise, we'll continue from here. Okay, if no one has any questions, we'll just continue from here. So, basically, multiplexers are, special cable connections that you can make. Multiplexers are used to multiplex connections, as in, like, let's say that you have like a switch that you want to turn on and off, but you want to provide eight people with the ability to be able to turn on and off that switch. So then you can use a 1 to 8 multiplexer that will, provide an expanded box for, different people to do the same instructions. So you do this multiplexing so that you can skip certain steps, execute certain steps, and do things in parallel. So, and then finally, all of this is happening, but in the design that we have above this first CPU overhead slide, here there's a problem. What if there is a loop, or we have some instruction which we are not sure how we are going to execute it? So you need to make decisions, right? You need to make decisions. So to make that decision, you need something called a control unit. So we add in that control unit to the processor, to the CPU, and this control unit connects to basically all of the units so that it can make decisions on whether to load something into the register, or load something into the data memory, or to load something into the ALU or not, right? So that's one thing. So again, very basic logic design. This is also something that you might have studied in high school. Is information is encoded in binary. Low voltage is zero, high voltage is one. Uh, one bit wire per bit is there. So uh, like basically there are AND gates, OR gates, NOT gate, NAND gate. Uh, Most of the logic that is there for flash memory is NAND memory. So that's why it's called NAND flash. There is also some NOR memory, but most of it is NAND. So there are sequential elements in a chip, like in a processor, that store data in a circuit. So this is like that store data one after the, like, based on falling or rising clock pulse. So if a signal is going up, it's like a rising signal. If the signal is going down, it's a falling signal. And based on that, data is stored. So uh, there there's various ways, you can clock the processor. So this clocking methodology is important because that sort of tells you when one cycle of the processor is ending and when another cycle is starting. So one way is that if you look at this graph going up and down, one way is you can measure it between these edges, like from this vertical line to this vertical line, or you can measure it like, change between one state to another, and the longest delay that happens, that is what determines the clock period. Basically, if you have like 10 different instructions, so 9 of those instructions take 1 nanosecond to execute, but one of those instructions takes 3 nanoseconds to execute, then the clock speed of your processor will be limited by that 3 nanosecond instruction because that's the one that takes the longest to run. So, so for for a processor, the first thing you have to build is a data path. Now, a data path is elements that process the data or addresses. So you have addresses. Addresses are locations where memory is stored, as you know. If you studied pointers, C pointers and all, right? You have to pull the data from an address. So you might have to do arithmetic operations on pointers to figure out where data is. So elements that process this data and address the CPU, those are the elements that build up the data path. So the first step is always the instruction fetch. So here we have taken a simplified view of the processor. You have 32-bit registers. So can anyone here tell me what a 32-bit register means? Or what 32-bit means here? Anyone?
In size of the register by like it can store that many number of bits.
It can store
Ba-
values from
yeah,
Like
it
it
can
can
store
maximum
values
minus
store
2
from.
to the
32
power
bits
To the power
data.
of
31,
32.
2 to the power 31 minus 1.
Yeah. So basically, it's the limit of the max size of the memory that you can address. So basically, if you have 32 bits of memory, like let's say you have a 32-bit processor that can deal with 32-bit address spaces. So the max memory that you can address is 4 gigabytes, which is 2 power 32. Basically, what that means is each of your memory locations has to have an address, right? Your address starts at 0 and it goes from 0, 1, 2, 3, 4, 5, 6, whatever. So the last element will have an address of something 2 power 32, whatever. So that 32 bits is the number of zeros and ones that you can store in that register. So you can only point to an address, that address can fit within those 32 zeros and ones. So a 32-bit processor can address maximum of 4 GB of memory. As you know that today almost everything has more than 4 GB of memory, even your mobile phone. So most operating systems and processors have moved to 64-bit. And no, we will not be needing 128-bit computers anytime soon, uh, um, because the 64 bits is very, very big. It's not just twice as big as 32 bits. You're raising it to the power, right? So 2 power 64 is a much bigger number than 2 power 32. So you do an instruction fetch, like you have to get the next instruction from the top. So now you have multiple ways that you can fetch instructions. Okay, there are R format instructions which read two registers, perform arithmetic, and write the result. So R format would be something like, let's see here. Uh, yeah, so yeah, here. So something like you have move. You have R15 for register 15, RBP for uh, something else. So imagine that if, yeah, RDX is also a register location, R14 is also a register location. So both of these are registers and you're like moving the number into something else. Let's go back to ARM so that we have uh, like the same three address code that you see there. So basically, whenever you see any representation where you have like assembly instructions which are represented using, let me pull out some example here. So yeah. So for example, here you have one register, one value and one instruction. So this is like a three address code because there are three parts in it, right? So let's go back to our ARM example. So here in ARM, you can see here. So move R6, R10. So here you have two registers only, and like you're taking a register value only and manipulating that directly, as opposed to this where you are comparing the register value with the number zero. So this hash zero is not a register here; it is literally the number zero. So this is something known as an R format instruction, which is like you read two registers, do some math on them, and you write the result also to a register. Then there's load store instructions. So load store instructions because you have to read register operands. So basically, let's say that the data that you need is not already in the register. And that's very common, right? Because your registers can store only like what, 64 numbers, 32 numbers. Obviously, a modern day program is a lot bigger than that. So you have to get the data from somewhere, right? So where will you get it from? You have to get it from memory. So this is where load and store instructions come in. So load is basically the instruction that loads the data from memory, and store is the instruction that stores the data back into memory. So read register operands, they calculate the address. So here in this, again in this instruction, you can see that there are relative addressing modes going on, where it's telling you the position relative to one particular instruction. Like SP here is the stack pointer, and it's 112 from there. So it's giving you some calculation. So you're doing math here, and from the offset. So there are load and store instructions. Then there are obviously branch instructions. This is basically just an overview of what the different kind of assembly instructions are. So here you read register operands, you compare operands, and reading and comparing, as in you have to check loop conditions and other such things, and you calculate the address. So finally, so yeah, branch instructions, you might have to jump to another address. You have to calculate where you have to jump. So first cut data path. So this is a basic data path that we have here now. It can do one instruction in one clock cycle. So, but the problem is that what if you need to read some data and you need to write some data in the same clock cycle? Ideally, we want all our instructions to take one clock cycle, correct? We need one clock cycle for every instruction. But what if there are instructions that involve loading and storing data? So first you will have to load, and then you have to wait until that data is loaded and operations are performed, and then you'll have to store it, because you are fetching the data from the memory. You cannot fetch data from memory and write data to the same memory in the same clock cycle, right? That will just that you cannot do that, because the clock hasn't ticked, right? You have to first get the data, and then a period of time has to pass before at least one clock cycle has to pass before you write it back, because otherwise you'll end up in a condition where you can have non-deterministic cases where you're reading the data before writing it, or you're writing the data before reading it. So the way to solve this problem is we have separate memories for instruction and data, at least on MIPS. So we create an instruction memory and a data memory. So here you can see registers, and here you can see the data memory. So the full data path comes out to be something like this. You have the program counter, which pulls the next instruction. It reads it, and then it reads like that instruction has to be decoded. The program counter just gets the instruction like load, add, sum, mul, whatever. It doesn't know what that instruction does. The instruction memory is actually responsible for reading that instruction, and it's I mean, the next step is your instruction decode. Okay, so now your program counter has read the data, but now you have to figure out what it means. The processor has no intrinsic idea of what a subtract instruction means or a multiply instruction means, right? Somebody has to tell the processor. So you have an instruction decode step that comes in after that. So this is the full data path for this is how the data path looks. So after instruction decode, you have execute. So now you have read the instruction, you have decoded the instruction, and now you know what you have to do. So based on whether it's an add instruction, you might have to do some math. So if you have to do some math, you will do execute, and executing on the instruction will mean like literally doing the math, adding the numbers, subtracting the numbers, comparing the numbers. And then there might be a write back, as in you have done the math and now you need to store the result of that math. And finally, you cycle back to the beginning. Okay. So you have various control fields, load store, you have branch instructions, you have R type instructions. So uh, basically, like this is the part where you can, if you read through this section, it's basically on how to convert assembly to zeros and ones and read them. So this is something that you'll probably never need to do because you'll always have the assembly on hand. But it explains why certain assembly instructions are looking different than others. So if you see like some instructions like over here, which have like three fields, like here we are adding one to R7 and adding it to R4. So here there are four fields, but here there are also fields where you have like only two numbers. Like here store is there, so store is just two entries instead of like four over here, right? So it's very different. Why is that? Because there are different types of instructions. So you have four fields. So here your R type instruction has these fields. The first one is which instruction. So zero here represents add. RS, RT, RD represents the three registers. So this is the final register where the number has to be added. So over here, if we go back to our example, yeah. So this is the R1 here is the destination register. This R2 here, SP is the other register, and this is the third value, which could also be a register in a normal program. So you have three registers, then you have the shift amount, which is how much to shift a number by. Usually this is empty, and finally the function field, which is a modifier. So you can club together some of these entries to make other instructions that are more complicated. Like for example, you might have an address. You might have to your processor might need to access some address, right? With that address might be big, so it might not fit in like bits. 5 bits means you can only access something that is like 32 numbers away, up or down, and that's a very small range. So you might have to access an address beyond that. That's why you combine these instructions into more complicated instructions. So then you once you add in the control lines and all to actually be able to do like a loop instructions and if conditions and all that, you end up with something like this. And it's already looking quite complicated, but that's because modern day processors are very complicated, right? So you can implement jumps. So jump instructions are very simple because you only need two things. One is the jump keyword itself, and the other is a very large address for where to jump to. So jump instructions are very simple. So they're an example of they're not an example of R-type instruction. They don't involve registers. They just involve addresses. So the process problem with this kind of processor, and this is like the design of the very first processors, is that the longest delay determines the clock period, and you can only execute instructions in one line, like in a linear order. Now, this is a very big problem if you want to do anything because your program is kind of heavily constrained. It can't run really fast. So you're not making the most common case fast. So we can improve the performance by something known as pipelining, right? So pipelining is very cool and it can be explained by a very simple example. So let's say that you are one person that takes 1 hour to dry, like wash certain amount of clothes, and then those clothes take 1 hour to dry. So you take a total of 2 hours. So now if I have two people and you split the load of clothes in half, how long would it take for two people to wash the same amount of clothes? Anyone? If one person takes like 1 hour to wash like one load of clothes, then if you have two people instead of one person and the amount of clothes is the same, how long will it take?
They divided by half.
Yeah, divided by half. That's it. You'll just divide it by two, right? It'll take 30 minutes. If you have four people, it'll take 15 minutes. Obviously, at some point, it will break down. If you have infinite people, it's not like your clothes will get washed instantly. But yeah, you can basically double the number of people, increase the number of people, and you can get a speed up. However, it's held back by the fact that there are some steps that take time to do. Now, let's say that you have 16 people or something. Not 16 people also. Let's say you have four people. So four people would be able to wash the clothes in 15 minutes. That's true. But clothes are still going to take an hour to dry. There's no way to speed that up, right? So the idea behind pipelining is that by breaking down the execution of programs into smaller parts and running them parallelly, we can improve the performance. And the example of what I gave just now about washing clothes and drying them, where drying is the fraction that cannot be parallelized, is something known as Amdahl's law. Okay. So in the MIPS pipeline analogy, there are five stages. You have the instruction fetch, which fetches the instruction from memory, instruction decode, which decodes the instruction and you read the data. Then you execute, as I said, you do the math. Memory is to again load or store the memory, and write back is to write the result back to the register for the next instruction. So again, here you can see some examples here that if the time for stages is 100 picoseconds for a register read or write, or 200 picoseconds for other stages, you can see that if everything takes 200 picoseconds, the total time taken will be 800 picoseconds. Now, if the program is pipelined, then it takes only 200 picoseconds. So this is the cool thing, and it's kind of magic really, because you wonder how, right? So anyway, the way it works here is that you have, or ideally in a single cycle, this thing you would have instruction fetch, register allocate, execute, data access, and again write back one after the other. So this whole thing took 800, then the next one took 800, then the third one took 800. It would take 2400 total, right? 2400 picoseconds. But if you pipeline it, then you can start it in multiple this thing, and each extra run will take only 200 picoseconds extra because they're overlapping, right? After the first instruction here is executed, you can start another parallel run, and it will take only like 200 more because it's just started 200 after here. So you can keep pipelining the instructions one after the other, and they will keep executing faster. The only challenge is, of course, that you should be able to pipeline them, as in, if the instructions are some hard condition that they have to be executed in one particular order, then you are out of luck. right? You can't do anything. You have to eventually wait for all of the data to arrive, rearrange it in the right order, and then fix it. But still, whatever time you saved up by pipelining, that is still time that you have saved. So if all the stages are balanced, if all of them take the same time, the time between instructions that are non-pipelined by the number of stages is the speed up that you can get. So one way to make this above pipeline even faster is if you could break it into 8 pieces instead of 4 pieces. So because then you could stack them, and then the each particular stack would take only like 100 picoseconds more. If they're not balanced, then the speed up is less. So the speed up is due to the increased throughput. So basically, you're able to do more things together. The time that each instruction takes to execute is not changing. Like over here also, each instruction is taking 200 picoseconds, and here also each instruction is taking 200 picoseconds. It's just that in one slice of time, you're able to do more things, right? So that's why where you're getting the speed up from. So the MIPS ISA, the instruction set architecture was specifically designed for pipelining. All the instructions are 32 bits. They're easier to fetch and decode in one cycle. Uh, and they're written in a very regular format. Like, let me see if I have some MIPS compiler here. Yeah, I have MIPS clan. Very good. So let's see. Let's run this through that and let's see what it goes like. What's this? Warning. Okay. File is not found. We can just remove that header maybe. Don't know. I asked ChatGPT to generate this. So maybe it gave me something that's not portable.
मोस्ट प्रोबेबली भैया हेडर फाइल वगैरह का कुछ इशू होना चाहिए।
हाँ, हेडर फाइल कहाँ डाला है? मैं भी देख रहा हूँ। I'll ask ChatGPT to write a simpler program.
या फिर भैया शायद एक हेडर फाइल डाल दोगे अलग से, उसमें मिसिंग है शायद। अगर हेडर फाइल डाल दोगे हो जाएगा।
चलो रुको, मैं लिखवा देता हूँ इससे फिर से, तब तक क्या ही है।
ऑल्सो भैया ये पूछना था कि पाइपलाइनिंग मतलब हम लोग कोई प्रोग्राम को पाइपलाइन कर रहे हैं तो
हाँ।
उसके उसके भी तो कुछ ट्रेड ऑफ्स होंगे, लाइक ब्रेकिंग अ प्रोग्राम इनटू सम पार्ट्स। तो
I mean, so there are two things that you are making an assumption here. One is that this is not software-defined pipelining. This is the pipelining that your processor is doing. It's independent of the code you write.
मेक सेंस नो।
Like, like here you are not that pipelining. What you are talking about is software wala pipelining. And yes, there are a lot of trade-offs. There are a lot of problems with pipelining. There's an entire section on just that. So let me see if this compiles here. This also is throwing some error. अच्छा यार, इसमें तो user include Linux. अच्छा, इसमें looks like okay, MIPS Clang is the C compiler or what? Let me see if MIPS GCC works. Ah, okay, great. That worked. Nice. So here, this is the MIPS instruction set. So this is the same instruction set that's there in the book. So here you can see that everything has three like there are add immediate unsigned, this one is store word equal. So everything has exactly 4 parts. Like store the value in this first one, take this and these two and store it in the first one. Here, take SP and minus 40 and add the both of them and store it in SP. So everything follows the exact same format, and this makes it very easy for it to be pipelined. Okay, so there's no variation. Like let's say that if one instruction is like you saw in x86 that we have a jump instruction that is just jump and one address, which is like basically like two format. Then you have three format, four format. So all are varying length instructions. So that makes it harder for the processor to know when to stop, right? But for MIPS, everything is in the same thing. So it's all very simply designed for this thing. So again, now you have a whole set of problems with pipelining, which is hazards. So these are situations that prevent starting the next instruction in the next cycle. So there are three types of hazards. Okay, one is structural hazard, one is data hazard, and the third one is control hazard. So the structural hazard is the simplest one to understand. Like let's say that you are over here. Now you have this register read. Okay, here you have this register read over here, and you have this register read over here, right? So imagine that these were more closer together. You have some instruction that depends on this computation, and you have to basically read and write to the same the register at the same time. Basically, you are trying to do instructions in parallel, and you end up with a scenario where you are reading and writing to the same location at the same time. So that is physically not possible in the hardware. So load store requires data access, and instruction fetch will have to wait, right? So you can't do anything. So the way to solve structural hazards is you can never solve it in code. You have to build your hardware to avoid structural hazards. So you have separate instruction and data memories, separate instruction and data caches. Then there are data hazards. And man, these data hazards and are a very big favorite topic among, like, pointer analysis has a shit ton of data hazards that you need to worry about. So here you're doing add the contents of temporary register 0 and temporary register 1 to register S0, and then subtract temporary register S0 value from temporary register 3. Now, uh, now think, now what will happen if this sub instruction executes before the add instruction? What will happen?
S not, I mean S0, there is no value in S0.
I mean, even if either there'll be no value in S0 or it will be a wrong value of S0, right? Your
Garbage
program
value.
your program wants you to first add two numbers, take the result of that addition, and then subtract it with another number. So if you execute it in the wrong order, then you'll do math on the wrong number, right? It's the value has not been updated. So basically, here you can't parallelize these instructions in the sense that you cannot execute them in parallel. The add has to execute before the subtract. Otherwise, the value will be wrong. Is this clear, or is someone still confused about this?
Clear, भैया.
You have
Clear,
to
bhaiya.
do it in one order. So whenever you have to do something in one order, you are limiting the parallelism. So one way to do this is to forward the result. So this forwarding is again done in hardware. So you don't do anything here. For software also there is solutions. For software, there are solutions is if you have like a very big loop or some other instructions in between that are irrelevant to these things, you can put those kind of instructions in between. Your CPU can reorder, the compiler can reorder those instructions to avoid those hazards. So compilers try to do this wherever they can, but the forwarding solution is that like basically you have instruction fetch, instruction decode, compute, and then you write back and then you store it in the register, right? So instead of that, as soon as you calculate the value here in execute stage, you forward it to the next part, like immediate forwarding. You don't wait for like storing that or anything. So don't wait for it to be stored in the register. Don't wait for it to be written to memory. So here, this will save you from such hazards to an extent at the cost of increasing the complexity of your hardware. So load use is again, if value is not computed when it's needed, because again loading the data involves the memory, and that is obviously going to be slower than register level operations. You cannot go backwards in time, so that hazard will still be there. So here is an example of code scheduling. So now this is the type of intelligence that you can build into the compiler to avoid this kind of shit. So you have to reorder the code in order to avoid the result of this thing. So the C code for A is equal to B plus C, and then C is equal to B plus F. Load, add, and this thing. So basically, you can do all of the loading in parallel, right? You're loading it on different registers. You're not loading it on the same register. So you can do that in parallel. And you can also do the addition in parallel. You don't have to worry about that. So just by moving the order of the instructions around, you can get like a speed up and avoid this hazard. So we went from 13 cycles to 11 cycles. So the processor would have to wait here for 2 extra cycles, but now it doesn't have to wait because like it can just go ahead and start. So this kind of intelligent rescheduling or reordering of instructions is done by the compiler. Now, control hazards are a very special kind of hazard, and it is the source of a lot of vulnerabilities and a lot of complexity and a lot of things in processes, which is here the problem is that your branch instructions determine the flow of control. Now, let's say that you have a for loop that's running 1000 times. So you have to fetch the next instruction every time. You have to decide whether should I upgrade, stay in the loop or break out of the loop. You have to compare two numbers, right? Either the condition that you're comparing inside the loop is true, or the condition that you're comparing inside the loop is false. So based on that, you have to execute the next instruction. Now the problem is until and unless you check that condition, you cannot know whether it will be true or false. And this is a very big problem for parallelism because you cannot parallelize instructions when you don't know what the next instruction is going to be, right? So the only way to do this is again, you have to wait. I mean, the naive way to solve this is to wait. Like literally, if you have a loop condition that you have to check, your entire processor waits until that loop computation is done, and then you go ahead and you fetch the next instruction. So now the problem is that this is very, very inefficient. Let's say that we can go with a few assumptions that will help our case here. One assumption is that very big loop, like most loops, run more than they don't run. Like the condition is true more often than it is false. Like let's say if you're doing for I is equal to 0, I less than 1000, I plus plus, for 999 times that loop is going to be true. Only once it's going to be false. Correct? Or like, mostly the loop will be true. So we can go with that assumption. The other thing is that each time you're checking, you have to do three things. First, take the current value of I, compare it with the condition, and then increment the value of I. So if you have like I is equal to 1 and you have to do 1000, you have to execute 3000 instructions. And that is a lot of instructions, right? A lot of checks. So you can avoid that by not checking it, by assuming that the loop is true. So basically, only stall if the prediction is wrong. So what MIPS does is it will do branch prediction, and this branch prediction is something that all modern day processors do. This branch prediction is something also known as speculative execution. The CPU doesn't know if the loop is going to be true or not. It just keeps running the instructions, going further and further and further. If it figures out that somewhere it is wrong, then it will backtrack one step and it will go ahead and execute the correct series. So you will face a penalty, obviously, because like let's say that I will become 1000 in the last one, and you go to, assuming that the condition is true, but then you realize that, oh, okay, I was wrong, and it will go back. So the penalty is like 2 or 3 cycles, right? That's much better than executing 1000 instructions sequentially. So this branch prediction is also can also be done dynamically, and you can use branch prediction to improve the performance of your programs. So let's say that you are writing a basic C program whose job is to figure out the first character of uh, the first letter of each sentence or something. So statistically, the naive way to do that is just do if the first str of 0 is equal to A, then return A. If it is B, return B. If it is C, return C, whatever. You are checking one by one. But if you take a look at statistics, then the most common letter in the English alphabet is E. So the E case should be the first case that appears. So if you're going through any book and you start with a random word, chances are is that you will hit E earlier than you hit any of the other letters. So just by knowledge of the input, you can reorder like your conditions to have more efficient branch prediction so that you make lesser comparisons before you exit the program. So static branch prediction is based on just like loop and if else. Dynamic branch prediction is what I gave, which is based on your inputs. So for dynamic branch prediction, you need to actually run the program and look at the outputs before figuring out what is the optimum sequence. This is also why some programs are slower on the first run, then they become faster because your CPU or your processor or your compiler basically runs from, not your compiler, but your CPU basically learns from previous runs, as in it caches more data and it knows. So you can build up state and you can use the advantage of dynamic branch prediction to get speed ups. So basically, pipelining improves performance by increasing the throughput. There are multiple hazards such as structural data and control, and instruction set design affects the complexity of the pipeline implementation. So I think this was about an hour. We covered only 4 or 5 slides, but this is something that is going to take many days. So in a day or two, again we'll meet up and we'll continue from there. So finally, if anyone has any questions or comments, we can take those and we can wrap up.
भैया
Yeah.
सो लाइक आप बोले जो हम जब भी कोई लूप चलाते हैं जो बस लाइन होती है वहाँ पे डेटा पहले स्टोर होता है, प्रोसेस होता है, देन
हाँ
वापस से रिटर्न होता है. So
हाँ
is that the reason why we use loop optimization like loop fusion and all in LLVM?
yes, it's the same reason. That the thing is that loops are the most costly operations in any program. If you optimize loops, then you can make the program a lot faster. Like there are like basically there's various things. For example, there's one optimization called loop invariant code motion. So let's say that you have a loop, a large loop. Inside loop, you're declaring a variable a. You're assigning it the value 10. So, and then you're using that a somewhere and in some other expression, and you are just continuing. So now the problem is, because that a is inside the loop, you are assigning that value like 1000 times or 10,000 times. Just by moving that a outside the loop, you can save that many like assignments of a. So the compiler just moves it out. Whatever code is unchanging inside the loop, it will move it out of the loop. Basically, like again, if you're adding up some numbers or something, and the only thing you're printing is the final value, then the compiler will just move that out and print the final value. So that is one example. Then there is loop unrolling, like where you know that each loop is going to, like, you know that a loop is going to run only 5 times or 4 times or something. So rather than check the condition each time and increment it, you just open up the loop and you print the statement 4 times. So printing 4 times is easier than like checking the condition, incrementing the variable and printing it 4 times. So then there is inlining, there is fusion, there are many other optimizations, but basically the entirety of high performance programming is reducing the complexity of code. I think anyone that does DSA very regularly will also tell you that the entire concept of time complexity is also hidden inside loops only. So yes, all of this is about loops.
भैया एडिंग टू दिस हम लोग लाइक जब लूप्स में क्रॉस इंडेक्स रेफरेंसिंग होता है मतलब i-1 या i+1 होता है तब ऑफ कोर्स वी अवॉइड सिमडिंग दोज लूप्स तो
Yeah.
देन ये लाइक हम लोग यूजिंग सॉफ्टवेयर ही शेड्यूल नहीं कर सकते क्या रादर देन लाइक पाइपलाइन आई मीन पाइपलाइनिंग करने से बेटर है कि some parts could be scheduled using software itself, right? या फिर लेट अस से हम लोग ऐसे कर रहे हैं कि कोई स्कोप लेट अस से कोई स्कोप से जंप गो टू यूज कर रहे हैं जंप कर रहे हैं किसी और स्कोप में व्हाट इफ वो स्कोप पैरेलली प्रोसेस हो रहा हो देन लाइक हम लोग ये चीज सॉफ्टवेयर से शेड्यूल करते हैं या किस तरीके से ये शेड्यूल होता है
So this is one of modern day processor. So the answer to this is very stupid and you will not like it. The problem is that the processor has no idea what the compiler is doing. Okay. So I'll explain this. I'll share my screen again and I'll explain this. So there was this project, and so this there was this entire process, like basically sometime in the early 2000s. Okay, Intel decided that modern day processor design is becoming very complicated. We can get a faster processor by making a processor that is compiler aware. Okay, which is what you are describing, that
या
in
राइट
software we can define certain optimizations, and then the processor will carry out those optimizations in that order. But unfortunately, they developed the processor, they sold it, and the people that they assumed that the compiler writers of that time would be able to write a compiler that could exploit the features of the processor that way. But unfortunately, it would not, it did not happen. The problem that happened was that the compiler writers of that era or compiler design in that era was not advanced enough to be able to take advantage of the hardware that is designed around compilers. So basically, this is a topic known as hardware software co-design, where you sort of think of the concept of uh, designing hardware and software together to work synergistically. But this is not what happens in modern day processors because Itanium got abandoned. Okay, so in modern day processors, basically your compiler will try its best to arrange instructions in a certain order, in a certain way that will avoid hazards, that will avoid stalls, that will avoid security vulnerabilities. But the problem is once the compiler gives the final set of instructions to the processor, the compiler has no control over how the processor runs the instructions. Basically, the processor can use the concept of superscalar execution to again reorder those instructions, or basically the compiler can give the instructions in one order, and then the processor can reorder it itself. It can ignore whatever the compiler is saying, and all modern day processors are like this.
So I mean, Itanium could be like better hit now rather than that time, maybe.
Yeah, but unfortunately, the problem is that there is a inertia, right? All of the world's software has been written for x86, and arguably now ARM also, since it has been around for 30 years. So every time you design a new instruction set architecture, you have to rewrite compilers, libraries, and tools and port everything to work on the new platform. So until and unless you prove that it can be like several orders of magnitude faster or something, it's not going to happen.
Makes sense.
It's not going to happen. So, yes, unfortunately, this blindness between hardware and software is something that persists even today. This is why compiler design is not deterministic in the sense that I cannot if processors executed code exactly as the compilers emitted them, then I could have a simulator for processors that I was designing like 4 or 5 years in advance, and I could see what speed up I'll get. Unfortunately, that's not how hardware works. The processor makes its own decisions. It decides which instructions to bundle together. There's this concept called VLIW, very long instruction word, where the processor basically takes 5, 6 different instructions, combines them together, and executes them all at once. Then there is multiple dispatch. There is the concept of multi-core processing and all. So all of these things are done by the processor independently with your compiler can only tell that okay, this is the best order of instructions that I have come up with. Now you go from here. So it is still there. So that's why uh, a simulator can never be as good as the actual physical hardware. You can come up with a compiler optimization. On paper, it will show you that this should result in optimal speed up. But when you run it on the actual hardware, it's how it performs is ultimately dependent on what the processor is going to do.
Yes, makes sense.
Yeah, and this is why vendor-specific compilers exist. Because if I work at AMD, then I have access to people who can tell me internals of the AMD processor that are not known to the general public, and we can build our LLVM based compiler in a way that takes advantage of those features. But the problem is open sourcing that would also be open sourcing your hardware design. So
Yeah,
yeah, it's also the reason why these different companies exist.
yeah, makes sense.
Yeah.
Yeah.
Is that the reason why we can like हम कोड कर सकते हैं for आर्डिनो का कोड हम सी में कर सकते हैं because आर्डिनो के पास सीपीयू है नहीं, तो वो आर्बिट्री इंस्ट्रक्शंस रन नहीं कर सकता. बट कैन वी राइट लाइक अगर मैं स्विच स्टेटमेंट लिख दूं, सो आर्डिनो को कैसे पता चलता है वो क्या प्रोसेसर से
I
रन
mean,
होता है.
see, the design of microcontrollers is very different from the design of microprocessors. Okay, the thing is, ki if you design a processor that will only take your instructions and execute them one after the other, like as I showed in my slide here, if you have like a completely deterministic processor, like this example over here, ठीक है? Here you are doing one thing. So here you have program counter, instruction memory, register, write, data memory, whatever. This is one after the other, correct? So here your processor is not trying to do any parallelism. It is not trying to do any like pipelining. It is not trying to avoid any hazards. It is just executing one instruction after the other. So in such cases, yes, your compiler is like whatever you feed it to the compiler is exactly what the processor will execute because the processor has no tricks. But the entire point is to improve the performance. We are doing pipelining and also to answer your question, something like Arduino is a microcontroller that is going to run one program in a loop and that is not going to do any compiler optimizations whatsoever. Like, any hardware level optimizations whatsoever. Arduino को तुम जिस order में add, multiply, load, store instruction दोगे, like whatever assembly or hexadecimal in this case you give it, it will execute the code in exactly that order. Like no hardware level optimizations are done because it's a microcontroller. So that is a different case. Of course, the Arduino has a processor. Without a processor, how is it going to work? The only thing is that that processor is very simple.
सुबह मेरा एग्जैक्ट क्वेश्चन ये था कि जो आर्बिट हम मतलब सी में अगर कोड कर रहे हैं आर्डिनो का, तो कोई आर्बिट्री इंस्ट्रक्शन मैं पास किया हूँ, तो आर्डिनो उसे एग्जीक्यूट कैसे करता है? बिकॉज हम कंपाइलर तो वही यूज करते हैं.
Compiler वही use करते हो, but you don't use the same compiler, right? That is also one point. Arduino's compiler is AVR GCC, and AVR GCC doesn't work the same way that your normal compiler does. AVR GCC, basically, you cannot. AVR GCC knows that you are compiling the code for Arduino for an embedded target. So it will not try to do any, like, basically, देखो, there are two things here, separate things here. One is the software optimizations that your compiler is doing, okay, which is like reordering the assembly or whatever you're doing on the side. And the other side is the hardware optimization. So here the fact that you're coding in C or MicroPython or C++ for Arduino is irrelevant. What is important is that Arduino's hardware does not support any optimizations. The hardware itself is going to execute the instructions linearly. So yes, you can take advantage of reordering instructions and you can take advantage of unrolling loops and all, but you cannot, the processor is not going to do any pipelining. There are no multiple cores. Arduino is a single core system. There are no pipelines, there are no hazards. So it will execute it one after the other.
Got it, भैया.
So basically parallelism, like as you can see here in Professor Govind's slides, maybe I'll show you a few slides to explain this concept. So parallelism is of many types. One is ILP, which is instruction level parallelism, which means the parallelism that you can exploit from assembly instructions. Okay. So here you have superscalar processors and very long instruction words. So basically vector add, vector move. So vector add allows you to add like 8 16-bit numbers in parallel. Okay. So if you give the vector add, if your compiler emits vector add, v add, it can add like 8 16-bit numbers or 16 8-bit numbers or as long as it multiplies into 128. So 8 16-bit numbers or 16 8-bit numbers or four 32-bit numbers or 264-bit numbers in parallel. So here the parallelism is coming from the instruction. Okay, it's coming from the specific assembly instruction. It's not coming from the compiler, it's not coming from the processor, it's coming from the instruction itself, because the processor is built in a way that it will take advantage of that parallelism. So this is one type of parallelism. Then there is thread level parallelism, which is taking advantage of multiple threads. So if your processor, every core has something known as, every Intel or AMD processor these days has either something known as hyper-threading in Intel, which is the marketing name, or AMD is simultaneous multi-threading. So here what they do is they divide the processor into two threads. So those two threads can execute in parallel. So this is thread level parallelism that you are getting for free from the processor. There are multiple cores also, which means you have more cores, just like more threads. Then there is finally task level parallelism, where you execute multiple tasks in parallel. Like you write your code in a way that that code has multiple things that are executing in parallel on different processors or different threads. And then finally, there are data level parallelism. So here is where your compiler optimizations and all come into play, where you have SIMD extensions, AVX512, AVX256, SSE, and all. So these are special assembly instructions that you can make your processor compiler output. And if your compiler outputs these specific instructions, then your hardware will be able to take care of them. So there are multiple different types of parallelism. Some parallelism originates from the compiler. Some of the parallelism comes from the OS also, in which and how it executes and arranges the various units, and some of it comes from the hardware itself. That's why you need to like read the entire, you need to know how the entire procedure works. We'll do an entire the session on this in the next talk that we have, which is probably like day after tomorrow, hopefully. But yeah, like I hope you got the point that there's like many different sources of parallelism. It's not just one thing.
Bhaiya, on the topic of looping,
Yeah,
let's say there's a very complex loop which has lots of variables which are dynamically changing.
yeah,
You told that there is, if there are some variables, you have to decide if we are taking it outside the loop, so
yeah,
that we don't have to like re initialize it again and again.
yeah.
So in this case of like complex loop with many variables, let's say that register spilling or something happens. How does the compiler versus the processor optimize it? For example,
It
like
will not
caching.
optimize it. It will not optimize it. That's the simple answer. So every single optimization has two concepts, right? One is the legality of the optimization, and one is the effectiveness of the optimization. A compiler or a processor will never choose an optimization that is whose legality is not proven. Basically, this is why pointer-based optimizations do so poorly, right? Like there is like if your code has lots of pointers, one magical way to write very slow programs is to like use a shit ton of pointers and alias them and like do some random stuff. Basically, if the compiler cannot confidently say if an optimization is safe in all cases, it will refuse to perform that optimization. The first order of business for any compiler is to produce correct code. Optimization comes second. So if you write very shitty code with lots of nested loops and lots of data dependencies and lots of conditional checks, the compiler will just not optimize that code. It's as simple as that. Yeah. So today's session came in like covering the basics of processor design only. But I think now that you guys know a little bit about this, we can go deeper into ILP and cache and all that in the later sessions. So don't know. I assume that the number of people will keep reducing as the meetings go on and become more complex. But I'm determined to see this through to the end. So, like, if you have any other questions, comments, or you want to talk about some general stuff, you can stay. Otherwise, you can drop off, and we can close the call. Anything is fine.
भैया जी सॉक से रिलेटेड डाउट है।
Tell me.
मतलब मैं एक और मैं P4 में कर रहा हूँ, उसका एक ऐसा प्रोजेक्ट है जिसमें और कोई पीआर डाल नहीं रहा, एक्टिव है और मेंटेनेंस करते हैं, बस उस प्रोजेक्ट में लोग पीआर नहीं डालते, मतलब लोग क्वेरी करते हैं बट पीआर नहीं आती। तो मेरी एक पीआर ऑलरेडी रेज है, उसमें मेंटेनर कुछ कमेंट्स करा है, मैं उसे सॉल्व कर रहा हूँ, बट होता क्या है कि एक दिन में वो एक ही बार कमेंट करता है, वो अच्छे से
तो
बता देते हैं कि क्या-क्या चीजें। तो मेरा डाउट है, मेरी एक और पीआर ऑलरेडी रेडी है, तो मैं उसे पहली वाली मर्ज होने से पहले डाल दूं या फिर वेट करूं एक मर्ज होने
if
का?
if it's unrelated to the first one, then you can put it.
नो, इट्स रिलेटेड, दोनों
As
रिलेटेड
in,
है।
is it compulsory for the first peer to be merged before the second? मतलब ऐसा कोई डिपेंडेंसी है क्या कोड में?
नहीं भैया, ऐसा कुछ नहीं है, बट द थिंग इज मुझे लग रहा है कि क्योंकि मेंटेनर्स उस पे सिर्फ मेरी ही पीआर पे वो डिस्कस आपस में भी डिस्कस कर रहे हैं कि क्या करना चाहिए, तो मुझे लग रहा है वो एक रेडी रखता हूँ, जब एक बार ये मर्ज हो जाएगी उसके बाद कर दूंगा।
So there is a polite way to do this. You open something known as a draft PR.
जी भैया।
So do you know what is a draft PR?
जी भैया, अभी कल परसों
हाँ
तुषार भैया ही बताए।
हाँ, तो a draft PR is a PR in which like necessarily all of your CI checks and all don't run. But उसमें क्या होगा कि if you put a draft PR, then there will be no pressure on your mentors to check it because they know कि draft है, अभी work in progress है. But it will signal to other contributors that you are already working on it. Because if you wait, right, for them to finish this, then one risk is there that somebody else will come and start working on that. And then you can just say कि यार मेरे IDE में solution बैठा था लेकिन मैंने community में डाला नहीं ना.
जी भैया।
You don't want that. So open a draft PR for the second issue. Don't assign it to any mentor. Don't assign it anywhere. Just open the draft PR, put the code there, and leave it for now. Then as
जी
soon
भैया।
as this PR gets merged, you move that out of draft and tag them.
श्योर भैया।
You can do that for as many issues as you want. 4-5 parallel में भी कर सकते हो.
थैंक यू भैया।
Like I think like वो git push करते समय there is some whip flag that is there that you have to add to make a draft PR. Usually जहाँ तक मैं जानता हूँ draft PRs will not trigger the CI also. So yeah. तो तब सब लोग निकल जाओ तब बाद में बात करते हैं आराम से.
जी भैया, हाइफन ड्राफ्ट करके अगर कर देंगे तो उस पे भी हो जाएगा,
हाँ
डायरेक्ट
हो
पीआर
जाएगा.
रेज कर दो।
हाँ कर दो उसी तरह से कर दो.
जी
Anything else? चलो तब okay. Good night guys.
Good night.
Good night,
गुड नाइट
Vinam.
भैया।
Good night, Bhaiya.